This video was inspired by Veritasium's video on p-adic numbers and my girlfriend, who somehow likes dimensional analysis in chemistry. Something about how it's like putting together a puzzle, I guess. Anyways, I just graduated high school, so the furthest I have ever officially progressed down the path of collegiate math was AP Calculus BC. A nice stepping stone, but still not far at all in the major scheme of things. But I was left completely confused by Veritasium's video on the p-adics. The math checked out, but all the ideas and uses were completely and utterly beyond my grasp to understand. Except for one, that the p-adics worked by zooming in ever closer onto numbers as an infinite series. This idea is identical to how a Taylor series works, so maybe by making a video on the Taylor series, maybe I could help myself understand the p-adic system, and maybe math in general, better. So, here it begins. This is the Taylor series, the quintessential operation that changed my worldview on mathematics. Here's a few common Taylor series. Confused yet? Good. Because I plan on working through exactly why they look so confusing and how they fundamentally work, how to build them, what their limitations are, and finally, a few of their uses and how they changed my view on math forever. So let's begin our deep dive. First, let's try to build a bit of intuition for a Taylor series. Imagine a car driving on a road. This number line will represent the current position of the car along the road. Now I will create three graphs: position, velocity, and acceleration, all as functions of time. There will be 5 time intervals. The car begins at x equals 0 with a starting velocity of 3 units per second. I'll also mark a few random accelerations that we can use to find the rest of the data. In the time interval 0 to 1, the acceleration is 0 units per second squared, so velocity will stay constant. Velocity is 3 units per second, so from 0 to 1, the car goes 3 units. We'll plot that on our x-graph. In the time interval 1 to 2, the acceleration is 1 unit per second squared, so we'd see an increase in velocity by 1 unit. This line is sloped though. Because I only want to deal with this problem in 5 discrete time intervals, let's pretend that it was an instant change in velocity due to the instant change in acceleration. Since the velocity is now 4 units per second, the car now goes 4 more units. Now let's repeat that same process for the third interval. And again for the fourth interval. Finally, for the fifth interval. Notice that for every single position value, you had to work from acceleration backwards for it. You had to look at acceleration to give you a new velocity, then the new velocity to give you a new position. Each piece of info stacked on the previous piece until you got your final result. That is similar to what a Taylor series does, but with 2 major changes. The first change is that we chose our time intervals as whole numbers. This makes calculations easier, but it isn't a Taylor series. A Taylor series subtly stacks the numbers at infinitely small time intervals until it's all one smooth function. The second reason is that we worked from acceleration down to position. Imagine we could reverse that using position information to deduce velocity and acceleration on our own. The only reason we couldn't do that here is because we had some random discrete points instead of a continuous differentiable position function. So, let's do another intuition builder that irons out these issues and really helps to verify the stacking aspect. We're going to use the same graphs that we had before, but this time we're going to define an actual function for position, x squared. So to begin, how would we go forwards from position to velocity? Well, velocity is just distance through time. Notice that this is another way to write the rate of change, or slope, of a position versus time graph like ours. So, if we could find an equation that represents the slope, we could graph the velocity. And that's exactly what derivatives do, track the slope of a function. What are derivatives again? Derivatives keep track of the rate of change of a function, or its slope. This graph's slope is 1 the entire time, so this would be its derivative. F prime of x equals 1, aka the derivative of f of x equals 1. Okay, well let's look at our position function then, x squared. I shifted it down 7 so it fit on the screen better, but this won't affect our answers, since the slope will remain the same no matter where the graph actually is. Let's just draw some tangent lines, aka slope-telling lines, to the graph at nice-looking x values and see if we can notice a pattern in what the slopes are. The first is at x equals -3. Choose 2 points along the line, do rise over run, and we get -6. Now, let's just repeat the process a few times, through to +3. It builds a predictable pattern. Draw a line through it, and we find that the derivative is 2x. Note that the -7 doesn't affect the derivative at all. So I can use 2x to find the slope of x squared at any point. Now we know what a derivative is, and that this function, x squared, has the derivative 2x. That means that the velocity function is just 2x. Now, for acceleration. Similar to velocity, acceleration is just velocity through time. So, acceleration is just the derivative of velocity. There's no need to do any calculus for this one though, since the slope of our velocity function is constant, too. In most circumstances, you don't have a computer graphing things for you. So let's pretend we didn't have any of the graphs drawn, and we just have this written information. How would we then calculate the position at any point, just given this data? Well, let's begin with the fact that x is dependent on velocity. This can be written like this. The bar above the v means constant velocity, and I'll address that later. The times time is to keep units straight. We need things in terms of just x, and the velocity is in terms of x over t. So by multiplying it by time again, you get rid of the t in the denominator, leaving you with just x units. Since this will be the equation we begin working on, we'll write it here so we can mess with it. The equation only works as written when velocity is constant though, hence the bar over v. Luckily, our velocity function is linear, meaning we can find the average velocity over our time interval, and use that as a fake constant velocity instead. But we're still not done, because now we have a final velocity component when we want this equation to give us a final position based only on starting values. How can we do that? Well, there's an equation for velocity that's identical to the position equation we just used, which looks like this. The equation only works with linear or constant acceleration, just like the previous equation, but our acceleration here is completely constant, so there's no other changes we need to make to our equation. We can just plug in this whole equation for v final. Now let's do some simplification. If you've ever taken a physics class, you are familiar with this equation. Each term in this equation has units that will cancel to x, so we know the equation will work to tell us position. And remember, we found this velocity and acceleration using derivatives. So in a way, the derivatives accounted for our units, and the t's brought them back to x. The derivatives stacked to provide more and more information to calculate position with. Well, this is almost exactly how a Taylor series works. You use derivatives to gain more information, which then stacks on top of one another to give you the actual answer. But a Taylor series generalizes that whole process without needing to rely on constants. How does it do that? Let's get a feel for how to build a Taylor series, first without relying on the equation. Here we have the graph of cosine of x. Let's pretend we never actually saw the graph itself, and all we know is this one point on the graph. How can we use this knowledge to try and estimate the next points on the graph? Well, we can find the derivative and use it to guess where the next point could possibly be. The derivative of cosine of x is negative sine of x, so at 3 pi over 2, the slope is 1. So let's go over to 3 pi over 2 and take a guess. Since the slope of cosine at this point is 1, the next point will be on this line, since the line also has a slope of 1. Notice that our estimate actually follows the graph of cosine for just a little bit before cosine veers off to the right. I'm going to mark the x-coordinates where our estimate matches with cosine using this brown line. Okay, well if the first derivative can get us accurate up to about there, what if we do it again with the second derivative? The second derivative is like saying, what's the rate of change of the slope itself? Calculating it is just taking the derivative of the first derivative. So, the derivative of negative sine is negative cosine. And plug in 3 pi over 2, we get 0. Well, we can't really create a line with slope of 0, and it'll become clear why in a second when I move on to the third derivative. The third derivative is the same process. Derivative of negative cosine is sine, plug in 3 pi over 2, we get -1. Okay, now to create a line using this number. We can think of the third derivative having the units y over x cubed. So to return the third derivative back to units of y, we can multiply the -1 by x cubed to cancel out the x cubed in the denominator. Our current estimation line is just y equals x, so let's tack on the -x cubed and see how that changes our estimation. Great. It's actually a little worse. That's okay, because this is a good intro to the part of the Taylor series we haven't discussed yet, the factorial. We need to divide by a specific factorial in order for the estimation to fit with cosine. Because we added the third term, we need to divide it by 3 factorial. Ah, that looks much better. We can actually use this estimate out to about this far now. Just to solidify what we already know, this line is us stacking 3 derivatives worth of information. And this is what that actually looks like in written form with the factorials included. It looks a little daunting, but if you look at it closer, it isn't that difficult. It's really just a derivative multiplied by x. The x looks complicated only because the -3 pi over 2 is what's shifting our orange line over to the yellow point. So let's focus in on a new point where the approximation holds to show how the equation works. First, we reference the first term. The red function at 3 pi over 2 is equal to 0, so we don't move our dot anywhere. Then, the second term. The red function's first derivative at 3 pi over 2 is 1, so the first derivative turns to 1. Then we plug in our x value at the green point, and now move our dot by that much. Then the third term. The red function's second derivative is 0, so it'll result in no motion like the first term, so we can skip it. Then the fourth term. The red function's third derivative is -1, so the third derivative turns to -1. Then we plug in our x value, and now move our dot by that much. And you can see how using these terms and drawing in more and more derivatives will slowly converge on the actual value itself. And this is all a Taylor series does. It stacks information from the derivatives of a function, and, in the form of a polynomial, settles on the actual value of the function itself. But we have one loose end to tie up. Why did we have to divide by that factorial? A Taylor series' basic job is to convert weird functions to simple polynomials by repeatedly adding the weird function's derivative information over and over. So, to address the factorial, let's talk about these basic parent functions and their derivatives. Notice the pattern? If you do, great. If you don't, how about now? The pattern is that every derivative takes the exponent on x, puts it in front, and then decreases that exponent by 1. The general rule looks like this. It works for all polynomials, no matter what the exponent is. It works on negative and fractional exponents too. It even works on each term in a polynomial independently, and just multiplies with the other coefficients already present. Basically, the power rule is a fact of life for polynomials and their derivatives. Since the Taylor series creates a polynomial, it needs to account for the power rule, and that's where the factorial comes in. Let's say we found a function whose fifth derivative at 0 was 1. Since Taylor series need to match the function, the fifth derivative of the Taylor series must also be 1. Here's a baseline polynomial that has the possibility of being the real Taylor series, but its coefficients can, in reality, be anything we need. We know this polynomial must have a fifth derivative of 1. So let's test that. Keep an eye on f, since that's our fifth term coefficient. Then we'll plug in 0, and set our two functions equal to one another. Solve for what our coefficient should be, and simplify down that disgusting denominator. Oh hey, it's a factorial. Repeatedly applying the power rule naturally makes factorials like this appear, and in order to cancel them out, we need to make our denominator the same factorial to cancel it. Think of it as like the price we have to pay to become a polynomial. If every derivative of our function is 1, then every term's coefficient would be its corresponding factorial. This matches with what the equation says, dividing by the nth factorial. Okay, so we've explained the basics of how building a Taylor series works and why the equation looks like that. The last mystery is the big R, which will come later. Now that we have the intuition under our belt, let's actually build a proper Taylor series now, using the equation as guidance. We'll build a Taylor series centered at 0 for this function, e to the 2x. First, let's find a few of its derivatives. We'll find the first, second, and third derivatives and do more if need be. Now, because we're centered at 0, let's find what the function equals at 0 for all those points. Now that we have a few solid derivatives, we can follow the formula, centered at 0, to enact our derivative stacking game. Our 0th term, no x or derivative to worry about, but notice the factorial is still there. Our first term, just use the formula and plug in the numbers we know. Our second term, same process. Our third term. This then continues on. Now this is the fun part. How can we use the patterns we see here to write the polynomial in series notation? I'll start us off with the obvious one. The exponent on x increases by 1 for every term. So we can represent that with an x to the nth power to show that, starting at n equals 0, the exponent increases by 1 every subsequent term. So the next pattern that's obvious is that the factorial in the denominator increases by 1 for every term, starting at 0. So we can put n factorial in the denominator. Those first two things were predicted by the Taylor series equation though, so they should have come as no surprise. Now, for the custom part, the derivative. The pattern is that for every nth term, it gets multiplied by 2 again. That is just like taking 2 to the nth power, and that's exactly what the pattern is. This is the Taylor series, centered at 0, of our function. So, let's see how our graph compares to the actual graph of e to the 2x. So first let's graph the normal function as is, and then make it thinner so we can compare it to our series graph. Let's then graph the series graph, starting at only the 0th term. Now up to the 2nd term, 4th term, the 8th term, the 15th term, the 30th term, and as the terms approach infinity, this Taylor series will literally become the graph. And remember, it just started as a humble derivative stacking game. Perfect. Now we've learned how to build a Taylor series. So what are its limitations, and what's the deal with that capital R thing? Let's do another Taylor series example to dive in and see. We now have a new function, natural log of x plus 1, and new derivatives. Same rules though. I do encourage you to pause here and try to build the polynomial yourself. Okay, now we'll follow all previous rules, reference our equation, and build the polynomial. Okay, again, now the fun part, building the series itself. The derivatives can be simplified down into a better looking form, factorials. These factorials can then be simplified further by the factorial in the denominator, because factorials are just repeated multiplication. I also moved the negative sides in front. Now is the pattern more obvious? The denominator just increases by 1 for every term, and the sign flips every other term. So let's write our series. The sign flipping can be represented with a -1 to the nth power. Since the first term is positive, that first exponent has to be even, and it is, so it can be left like that. Wait, something's wrong. If we actually wrote out the first term from the series, we'd find it to be x to the 0th power over 0. That isn't at all what the first term is, and it's actually impossible and would break the series. Well, the Taylor series equation actually gives us free liberty to modify what the starting number is. It would work much better if we bumped up the starting number to 1 and changed the exponent on -1 to keep the first term positive. There we go. Now it perfectly matches our polynomial. And yes, a correct answer would also look like this if you really wanted to keep 0 as your starting point. But then some later math gets a bit more difficult, so try to keep your series as simple as possible. The exponent on the -1 and the starting point rarely matter in the long run. And this is the completed Taylor series for the function natural log of x plus 1. Alright, just like last time, let's jump on over to the graph and see how that compares. Okay, so here's the normal function. Now we'll repeat the same thing as last time and tack on terms bunch by bunch. First, the 0th term, up to the 2nd term, to the 8th term, to the 20th term, to the 60th term, to the 200th term. Okay, so something's not quite right here. No matter how far we go, the Taylor series doesn't want to approximate our function any further than x equals 1. This is no bug though, sadly it's a feature. This is the major limitation of a Taylor series. Some functions cannot be mapped through all x values by a Taylor series. But why? It has to do with the calculus behind a series itself. Take this list of numbers. What pattern do they follow? Each term is cut in half. In other words, their common ratio is 0.5. What if we wanted to write this in series notation? Well, we'll begin with 16 and say that every term after that gets multiplied by 1/2 n times. We have just written a geometric series. It is any series, an, starting with a starting number a and a common ratio r stacked over n times. In calculus, what's important about a series is whether it diverges or converges. In other words, does it go off to infinity or chill at some number L? Well, our series is an infinite stacking game, so the only way you can be sitting still with infinite addition is if, at some point, you're infinitely stacking zeros. So let's find that out. Grab the inside bit of the series, and then take the limit as n approaches infinity. Since you are basically multiplying 1/2 infinite times, this will push you down to 0. Since this limit equals 0, the series will indeed reach a point where it is infinitely stacking zeros, so the series itself will stop at some number L. The reason our limit reached 0 was because it was multiplying our common ratio, 1/2, infinitely many times. So whether or not the series converges or diverges is dependent on the common ratio. Okay, well what's the rule here? What common ratios result in a series that grows? 1's equal to or greater than 1. And what common ratios result in a series that shrinks to 0? 1's less than 1. Okay, but the Taylor series doesn't follow the geometric series notation. So how does this even matter? Well, we can mathematically compare the two, but we have to sort of abuse math to make the comparison. Let's pull up our original list of numbers again. How did we solve for the common ratio? Well, we divided any number in the series by the one that came before it. If we showed this in the proper notation, it would look like this. We can represent any number in the series with the normal geometric series notation, and we can represent the next term like this. If we then do a bit of algebra and simplify, it simplifies down to r. So technically, any series' common ratio can be solved like this, even if they don't follow the normal geometric series format. How exactly? Well, we only care about how the series will act as n approaches infinity, again looking for that final term to be 0. So if we take our formula for r, then take the limit of it as n approaches infinity, we can see what the common ratio will be towards infinity. And remember, the final term will only be 0 when the common ratio is less than 1. So we'll say that there. And now we have a completed equation for finding the common ratio, which we can use on all Taylor series, or any series actually. Now we can finally see what the problem is with that other Taylor series veering off at 1. Alright, armed with our new equation, let's see what the deal is with this Taylor series. First reference the equation, then plug in the n plus 1th term, and then the nth term. Because we will be hitting it with an absolute value later down the road, we can ignore the -1 multiplier. It will make the ensuing algebra easier. Rewrite the exponent on x, cancel out equal terms, simplify the fraction. Now, actually take the limit as n approaches infinity to get r. Now reference our condition, then plug in x, and finally make it a bit more readable. Okay, so our Taylor series can only approximate the function when x is between -1 and 1. One quick final note though. Once you get to this stage, there is a small chance that those ending values can create special cases that result in a working Taylor series still. This actually does happen to be the case for x equals 1 here, meaning it is part of the successful points, but I won't get into how it works since that would open a can of worms that could literally be its own video. These were the limitations I was talking about at the very beginning of the segment. Remember the capital R thing? That big R stands for the radius of convergence of a Taylor series. It just describes the values of x that satisfy a Taylor series around a certain point. So for this Taylor series, the radius of convergence is 1, centered at 0. And finally, we have completed all the parts of a proper Taylor series and discussed its limitations. So what are its concrete uses? And what can we learn about math from this? The use of a Taylor series is that it turns complex functions into reliable polynomials with some effective range that we call R. So instead of dealing with the complex functions, we can deal with their Taylor polynomials instead. It is oftentimes much easier for a computer to calculate a polynomial than to calculate a weird function, and it can calculate it much faster. When integrating, some functions don't have obvious antiderivatives, and aren't easy to integrate using other methods, so a Taylor series representation can make integration much easier. Taylor series are also just very good approximations when you look at a small domain. In physics, they will often have you replace cosine of x and sine of x with these approximations when dealing with pendulums, because the context of dealing with pendulums implies you're working with small angles, and therefore a small domain. These approximations come from, you guessed it, a Taylor series. And that's just a few of its more basic uses. When I first began making this video, the original takeaway I had for it was that math is a malleable tool, able to be molded in clever ways to help solve problems. And this statement is still undoubtedly true. But what I realized, above all, is that high-level math is not about trying to brute force learn more and more difficult operations, like progressing from algebra to calculus to group theory to chaos theory to symplectic geometry and so on, whatever so on is after that. You can just learn these things blindly, but it won't be easy, since you don't know fundamentally how the math works. The real lesson behind high-level math is discovering the different ways that math can be molded to help solve complex problems, which can only be taught by revealing exactly why and exactly how the math works. It's like learning to create those complex shapes using the tools designed to help make them, instead of with your bare hands. I found out that the real reason why I couldn't understand the p-adics very well was because I didn't realize that the p-adic system described a way to mold math that I just hadn't been taught yet. It's like showing me cookie cutters after never having seen them before, but not explaining how I can use them. The p-adic system was also, admittedly, a few stepping stones beyond my understanding of how math can be molded for it to really click though. And it still hasn't. I need to check a few more boxes before I revisit the topic. But the Taylor series was still a nice step towards it. So my real hope for this video is not to teach you about how a Taylor series works. It's to change the definition of what it means to learn math, and how a Taylor series is one of many genius examples of how math can be molded to solve problems, and only by unraveling how it fundamentally works can you see how genius it really is, just like with any other math concept.